Okay, so today we are talking about conditionality. Conditional probability is the probability of something happening after something else has happened. Okay. Okay. We're also dealing with situations where more than one event is happening, okay, whether they're related to each other or not related to each other. Okay? So let's talk about a simple example. All right. Um, what is the probability that the two children who are not twins are of the same sex? So what we do is, there are different ways of playing this. One way is to make a table. One way to do that is this. You could say, first is a boy, and then a boy and then a girl, and then a boy, and a girl, and then a girl. Okay, those are the only possible arrangements of the genders of two children. So when the probability, a probability is listed is as action of the solutions or winning scenarios that you're interested in over the possible you have. So the number of working situations, or situations that are of the answer that you're interested in this case, it's when both genders are the same, over the number of possible situations altogether. So a couple of things right off the bat, since the number of possible answers that work for you, your numerator, is going to be either equal to or smaller than, most often smaller than, the number of all possible situations, probabilities are small numbers. They're between 0 and 1. Okay, and we write this as probability of some event happening A. This is spoken as that's how you speak that, the probability of event A. Okay? So, in this case, the event that we're interested in is identical gender. So, the number of scenarios in this case is how many are identical gender? Only one? Two, boy, boy, and girl, girl. So there's is 2 all over how many possible situations? 4. Or 0.5. Okay? 1/2, 0.5. Okay? All right, so let's do one that's a little bit more interesting. What is the probability of rolling a regular 6-sided die and getting a prime number? So So, what are my prime numbers? What is the first prime number? Yes, 1 is not a prime. For the love of God, it is not a prime. Okay. Well, first of all of the possible scenarios are 1, 2, 3, 4, 5, and 6. And the number of correct working answers, or success answers, is how many? So there are 3 all over 6. Again, probability is 1/2. Okay? Okay. So now, if the probability of getting a prime number is 1/2, what if I rolled the dice 2 times? So I rolled it once, and then I picked it up. I rolled it once, recorded my answer, picked up the die, rolled it again, and recorded my answer. What is the probability that I got a prime number 2 times? So, first of all, this is where we're dealing with probability trees. So, the probability of getting a prime is 0.5, and the probability of a non-prime is 0.5. Okay? So we start off at that vertex there, and we have a choice, or we have odds. Half of the time it's going to go up, half of the time it's going to go down. Other examples will be different numbers, and we will go into all of those in a moment. Okay, so this is the scenario after the first roll. Okay? Now I'm going to roll again. Now, if I'm going into this reality, okay, this alternate universe, now I've rolled the die and I've landed a prime number. Great. Now I'm going to roll a die again, and it's still 1/2 for a prime. Okay? So the probability of rolling a prime 2 times is this path. Okay? So the probability is going to be multiplied because if we think about the possible scenarios, we've got 4 possible scenarios, and those 4 possible scenarios are, if you were to think about it as a diagram here, prime, non-prime, prime, non-prime. Okay, so if I roll my first die and I get a prime, I'm either here or here. This is a 50-50. And then if I roll the die again and I get another prime, it's here. So it's 1/2 and then 1/2 again, multiplied together. So it's 1/4. Okay? So the probability of 2 primes occurring in this scenario is 0.5 times 0.5, 0.25. Okay? So now we can go back and ask ourselves, let's go back to the problem we had a minute ago about the genders. Okay? So going back here, there's a 25% chance that it'll be a boy-boy, 25% chance that it'll be a boy-girl, and then a girl-boy, and then a girl-girl. Okay? So if we were to make that tree, all right, the 2 possible scenarios are boy-boy or girl-girl. So that is 1/2 times 1/2. Okay. And these others, of course, are 1/2 times 1/2. Final honest to God answer is 0.25 plus 0.25, because one scenario or the other will give me the right one. So 0.25 plus 0.25, 0.5. Okay? Who here took AP Stats? I think there's like 4 of you. Who took it? I got 1, 2, 3. Oh, that's right. She was the 4th. I thought there were 4. Okay, so the rest of you guys, have you seen this before?
Yeah, I think the block completes.
Okay. Yeah. Yeah, biology does very similar kinds of things when you're talking about genetics, probability of a recessive gene or all that stuff. So it pops up. Okay. So one thing popped in here. A lot of time, in this first example that I did about the boy, boy, girl, girl, in some scenarios I multiplied the numbers. In other scenarios I added the numbers. So how do you know which to do under which situation? The long and short of it comes out. If we have an and statement, you're going to multiply. If we have an or statement, we're going to add. It's a good general rule. And again, of course, there's always ways to rewrite your sentence and make it cryptic and weird. But if we were to look at this example about the gender roles again, I'm multiplying the 1/2 and the 1/2 because first I'm saying that it's a boy and then it's a boy again. Notice that I use the word and. Boy and boy. Girl and girl. So I multiplied the 1/2 times the 1/2. But at the very bottom there in blue, I said boy, boy, or girl, girl. So I added them then. Okay? Because there are different scenarios that'll work for me. Okay? So, can we, almost done? Okay. So, okay. By the way, this is sometimes called the sample space. Okay, the sample space is a fancy way of saying all of the possible scenarios. Okay, it's a nice fancy way of saying all of that. Okay, because I'm not going to get, I'm not going to get a 0 when I roll that die. 0 is not in the sample space. It's only going to be 1 through 6. Those are the only possibilities. If I have 2 dice, well, and I roll them up and I add up the digits, what's my sample space? 2 to 12. I'm not going to get a 1 because I can't get a 1 and a 0, and I'm not going to get a 15 because those digits aren't going to add up to 15. So my sample space is just the scenarios that exist between 2 and 12. Okay? Does that make sense? Yes? We good? Okay. Now, whoa. So, here's a fun one. Now, when I say stated, I mean not weighted. Okay, they're not biased dice or anything like that. They're like the normal dice you find in a board game. Okay? What's the probability of getting a 7? All right. No, if you 2 dice, add them up. Like you're playing a. Oh, I understand. But if you're rolling 2 dice and you're adding up the digits, what is the probability of getting a 7? Okay, so when you're dealing with this, what it might be easiest to do when you're dealing with like lots of possible arrangements, okay? Because you've got like 1 and 6 and 2 and 5 and so on. It's easiest to make a table, okay? Because you're dealing with two variables, the first roll and the second roll, okay? So let's make a table. So if I roll, so let's just fill this guy in. So we have 2, 3, 4, 5, 6, 7, 2, 3, 6, 7, 4, 5, 7, 8, 3, 5, 6. All right. So that would be the totals of my die rolls. Okay. So how many possible outcomes are in there? What are the, how big is my sample space? How large is that? How big? 36, because it's 6 by 6. So my denominator is 36. The probability of a 7 would be, well, how many times did we see a 7? 6 times. Okay. Now, what if I had said, what is the probability of rolling a 7 or an 11? Well, the key word that I used in there, what was it? Or. So the possible ways of successfully rolling the number you're looking for, either 7 or an 11, well, there are 6 sevens and there are 2 11s. So the number of ways of successfully rolling would be 6 plus 2 all over 36. I could have also said it this way. The probability of getting a 7 is 1/6. The probability of rolling an 11 is 2/36. So, thank you. Thank you. So, adding them up, I wind up with all over 2 ninths. Okay? Yes. Mm-hmm. Mm-hmm. Ah. That is the probability of a 7 or an 11. Okay, and this is the union symbol. We're just going to get to this in a minute. This is the union symbol. Okay? It's the probability of 7 or an 11. Now, we saw unions and if you took pre-AP geometry, you probably saw union and intersection. You guys remember that? Okay, so just we're gonna take a digression back to Venn diagrams for a second, so we can put this in a visual context. Okay. Okay. In this, now, this particular problem, if I were to talk about probability, this is the probability of a 7 and the probability of an 11. Okay, for a moment we have to say to ourselves, what does, it's the probability of rolling a 7 and an 11. Could that ever happen? Can you roll a 7 and an 11 simultaneously? No, because you only have 2 dice. So that intersection, this is called the intersection. That would be 7 intersect 11. Okay, the probability of both things happening is 0. Okay, so this example, this Venn diagram doesn't fly. I can modify my Venn diagram to deal with 2 events that are what we call disjoint. They don't have anything in common. There is no chance that both events will happen at the same time. Okay? So a better diagram would look like this. Okay? So if I were to, now the probability of rolling 7 we found out was 1/6, or 0.16 bar. The probability of rolling an 11, that was 230. Which is going to be 0.005005. Pretty sure that is 1/18. Oh, it's off by, no, it's the red is not that big. I think I'm also got a, yeah, I got a decimal point error. It's here. So a little more than 5.5%, and a little more than 16.5%. So if I were to take a dart and throw it, well, I have a 16.6% chance of landing inside the first circle, and I have a 5.5% chance roughly of landing in the second circle. Okay, so adding the 2 of those up, because either one of them will give me my answer. Well, either one of them will give me a win, so to speak, right? That's why we add them, because it's an or statement. It's land inside the first circle or land inside the second circle. I don't care which. Okay? So, in this scenario, we add. Okay? Does this make sense at all? Okay. So let's do one. Does that, first of all, is there anybody in here who's never played with a deck of cards? Because I hate asking these questions and people like 3 examples in, they're like, how many jacks are there? I'm like, oh no. Okay, so we all know what a standard deck of playing cards looks like, right? 52 cards, 4 suits, 2 of them are red, 2 of them are black, ace through 10, jack, queen, king, right? We all know what that it looks like. We good? Okay. So, let's talk about picking 2 random cards. Okay? Now, here's the important part. I'm gonna pick two cards. One at a time. So I'm going to pull a card, I'm going to look at it, I'm going to write it down, I'm going to stick it back in the deck, shuffle it, pick another card, record it, and put it back. Okay? Now that part about replacement is a really, really, really big deal. And whenever we're talking about a group like this, you have marbles in a bag, and you grab a marble, okay, and then you grab another marble. Do you replace it or do you not replace it? Is a question that should come to mind because that's going to change how many marbles are in the bag. Okay, so let's just say, for example, I pick a card and I get the ace of spades. Okay, well, what's the probability of getting another ace? Well, if I put it back in the deck, if I put the ace of spades back in, I could pull the ace of spades, the ace of clubs, the ace of diamonds, or the ace of hearts. I still have 4 possible wins for the second pull. But if I pull that first ace and I put it in my pocket, and then I pull another card, now there's not 52 cards in the deck anymore, and there aren't 4 aces. How many are in there? There's 3 out of how many? How many? 51. So, side question, just the probability of pulling that first ace is what? How many aces do we have? 4 out of a total of 52. And now, let's say I don't replace it. I put it in my pocket, or I'm building a hand of cards or whatever it is, and I like this card and I'm going to keep it. And I reach into the deck and I grab another ace. What are the odds now? 3 out of 51. And by the way, sometimes it's, especially when you're doing these problems and you're working in fractions, is to not reduce your fractions sometimes, because if you don't reduce your fractions right away, then you will oftentimes see that you have common denominators. Okay? So, like, for example, if I were to go back to this original question, see, so now this would be what I'm dealing with. So 12 all over 51 times 52, which is 225, big number, right around 2,800. And then you would reduce your, you could reduce it here, but we're not adding or subtracting, so we don't have to worry. Moving on. But now let's go back to this problem. So I'm not considering an ace as royalty. I know in some card games you do, but we're just talking numbers here. Okay? So jacks, queens, and kings only. All right. So if we look at this, we have an or statement. So we have 2 possible scenarios that are occurring, right? You could win by getting a royalty, or you could get a win by pulling a red card. Okay? So in the beginning, what is the problem with a royalty? There are how many royalties in the deck? There are 12. 4 suits, 3 cards, so 12 cards. So, and what's the probability of getting a red card? Say again? But what about getting a red royalty? Right. Okay, so let's not talk. Let's worry about one card pull. Okay. Let's talk about one card pull first. Okay. So if I had asked you, what is the probability of getting a non-spade or a non-ace? So what is the only card that's going to fail? The ace of spades, right? So you could succeed by 51 out of 52, right? It's kind of like old maid. If you get the old maid, the game's over for you. Remember? Okay. So if we were talking, this is a. So we have. Let's do spades, clubs, hearts, diamonds. Okay. And through 10, queen, king. All right. And everything in between. According to this problem, these all work, right? And these all work. Anything inside these regions is going to work. Does that make sense? I'm not sure if you're digesting or if you have indigestion. What's going on here? All right. So what we're going to deal with here is an added probability. We have both things occurring, okay? But we have to be careful about something because this section here is being counted 2 times. And we have to be careful of that. So let's go back to that Venn diagram. Okay. Oh, it's now. Okay, so the probability of getting a red card and the probability of getting a royalty are bad lettering. Probability of getting royalty and the probability of getting red are not disjoint anymore, are they? They're not disconnected from each other, are they? Because there are things that do both, right? So if we were to look and say, go back to the dart example, and if I were to throw a dart at this, anything that's inside this bubble would succeed, right? Agreed? So, the probability of a royalty was 12 out of 52, and the probability of a red card was 26 out of 52. The question is, how much is in here? How many red royalties? 6 red royalties. Okay. Now, what we have to be careful of is that intersection. By the way, this will be posted this afternoon. Okay. This. do 2 class periods from now. Okay, so this inner piece, intersection, never works for me anymore, is being counted 2 times, and we need to be careful, we need to be cognizant of that. Okay, so what we have to do is we have to take that out because we're counting it 2 times, you see? So what we have is 12 out of 52 plus 26 out of 52 minus 6 out of 52. Okay? So we can write this as the probability of event A and event, one or the other. The probability of A or B happening, one or the other, is the probability of A plus the probability of B minus that's a formula you're going to need. So, and here's an example of where keeping not reducing your fractions was useful, because now with all the same denominators, the math is a little bit nicer. So we're dealing with 32 out of 2 is the real probability here. Okay. Now, let's confirm that with hard reality. So we have okay, if we were to look at all of okay, we have 10 cards here. Oh, sorry, 9 cards here. And now 4 by 4, so we have 16 here. So 9 out of 52. Yeah, ace through 9 and then 10s. Oh, because these 2 10s aren't allowed. Right. Because it's not a royalty and it's not a red. That would be the 10 of spades and the 10 of clubs. 10 and 12, so 32 out of 52. 8/13. What? Oh. Oh. Okay. Do you see where I came up with this? So that formula is an important formula when you're dealing with combined events. Okay? Guys, whatever you're doing, stop. Okay. So, let's do a couple of quick examples, numeric quick examples, and we're about to run out of time here. All right, thanks for that fire drill. It was really good. Let's put 20%. So, the probability of event B is what we're looking for. One thing that I say to do is to put everybody into fraction form. If you can, it's sometimes nicer. Or if you don't have any repeating decimals, put it into decimal. This is 1/3, and what we're looking for. Okay? So, going back to that formula, we have the probability of the probability of the union. It's the probability of the first guy, probability of the second guy, minus the probability of them both. Okay? So now let's plug and solve for what we need. Okay. Oh, by the way, there was a term that I wanted to talk about that I should have said here. These are disjoint sets. They're also known as mutually exclusive. So mutually exclusive means if this one happens, it excludes the possibility of the other. Okay? So if you were born in the Western Hemisphere, that excludes you being born in the Western Hemisphere. Sorry, Western and Eastern. I think I misspoke. If you were born in the Eastern Hemisphere, that excludes your possibility of being born in the Western Hemisphere. Okay? Can't be born in both. Okay. Which one? Fourth. Okay. Yeah.
Like, the way I was thinking, like, since the A union B equals 2/5, couldn't we just subtract 1/3 from the 2/5 to get, and then this is finished? Why wouldn't that work?
Because you're not dealing with the left-hand side. But this minus this? Hold on for a second. This episode of the Ronco Show has been brought to you by Mutually Exclusive Events.